We begin with a haunting tale, Leonid Andreev's story of Lazarus, a man resurrected from death who carries something otherworldly back with him, setting the stage for our neuroscientific exploration of what happens when we peer into the abyss of dying. After Lazarus rose from the dead, his town celebrated, but joy soon turned to dread as strange, unworldly events followed him everywhere, eventually reaching the ears of Emperor Augustus himself, who summoned the resurrected man to witness the void in his eyes. Nietzsche warned us, when you look long into an abyss, the abyss also looks into you. So what happens when we turn the tools of neuroscience on this proverbial abyss, examining the dying brain through animal and human experiments? In 2013, Borjigin and colleagues studied 9 rats, inducing cardiac arrest and using EEG recordings to hunt for neural signatures of consciousness after the heart stops beating. They monitored electrical signals across the frontal, parietal, and occipital cortices, tracking brain activity at baseline, during anesthesia, and following cardiac arrest. The protocol moved from baseline recordings through anesthesia, then cardiac arrest induced by potassium chloride, and finally to data analysis searching for patterns. Researchers analyzed power density, global coherence, directed connectivity, and cross-frequency coupling, examining the data from multiple angles to capture the brain's dying dynamics. Within 30 seconds of cardiac arrest, a surge of synchronized gamma oscillations above 25 Hz swept the entire brain, showing front-to-back information flow and tight coupling with theta and alpha waves before everything went silent. These findings suggested that the mammalian brain possesses the potential for heightened information processing, possibly sustaining subjective events such as near-death experiences. But do these findings in rats translate to humans? In 2023, Zhu and colleagues examined EEG data from 4 comatose patients who died in the neurointensive care unit. Analyzing recordings before and after ventilatory support was withdrawn to identify neural signatures of human death. Contrary to expectations that the dying brain would go quiet from oxygen loss, results showed the human brain may actually become activated, with increased gamma activity throughout the cortex. The gamma surge manifested as increased absolute power, enhanced phase amplitude coupling, and strengthened functional and directed connectivity across the brain. This activity peaked in the temporoparieto-occipital junction, the so-called hot zone, critical for conscious processing, suggesting awareness-related regions light up during dying. However, only 2 of the 4 patients showed this gamma surge, and both had a history of seizures, raising questions about whether this represents normal dying or epileptic phenomena. The paper noted that both patients with seizure history showed persistently high gamma connectivity at the TPO junction, regions previously linked to out-of-body experiences in epilepsy patients, providing a potential EEG signature for this commonly reported near-death component. Much more research is needed to determine whether these oscillatory patterns reflect how the dying brain actually behaves, are statistical flukes, or are symptoms of a hypoxic epileptic cortex. A 2024 review by Mashur and colleagues explored potential neurobiological mechanisms underlying end-of-life conscious experiences and their place within neuroscience. The authors argued that a complete understanding of consciousness must necessarily account for these unique subjective episodes within the framework of neuroscience. One proposed mechanism involves a rapid release of neurotransmitters, glutamate, GABA, adenosine, dopamine, norepinephrine, and serotonin, flooding frontal and occipital regions during the dying process. The serotonin surge stands out dramatically, a 20-fold increase within 2 minutes of asphyxia, and a staggering 250-fold rise after 20 minutes. Activating serotonergic receptors in the brain is believed to generate powerful hallucinations, potentially explaining the vivid perceptual experiences reported during near-death episodes. DMT, the fastest-acting serotonergic psychedelic also naturally secreted in the brain, spikes in the visual cortex of rats following cardiac arrest, suggesting an endogenous trigger for near-death-like experiences. Remarkably, subjective reports of DMT experiences are often described as feeling more real than reality, qualitatively consistent with accounts of near-death experiences. Another network-level mechanism, called explosive synchronization, proposes the dying brain exists in a tug-of-war between chaos and order, as homeostatic processes fight to preserve functional architecture. As brain networks disintegrate from oxygen loss, homeostatic failsafes kick in to prevent complete collapse, creating tension between destructive hypoxic forces and protective regulatory responses. In this critical moment, the brain undergoes a dramatic sequence. Networks break down, homeostatic responses trigger, dynamic organization shifts abruptly, global connectivity bursts forth in high-frequency gamma oscillations, and then everything flatlines. A final model called percolation is based on random probabilistic events. Cortical networks disrupted one at a time by oxygen deficiency, like dominoes falling in unpredictable patterns. The brain percolates toward an inflection point marked by bare-bones scaffolding of interlinked hubs, at which point an extensive information discharge may ignite within surviving nodes. The temporoparieto-occipital junction, crucial for sustaining consciousness, emerges as a prime candidate for integrating information during this highly volatile period of minimal brain function. Ultimately, when the last remaining connection goes offline, the entire network collapses in a cascade, effectively shutting down the brain. To properly understand these neural biomarkers of dying, we need to consider some important caveats and limitations. Near-death experiences are not the norm. Only 10 to 20% of cardiac arrest survivors actually report having experienced such phenomena. In individuals who don't survive, it's impossible to cross-reference physical brain findings with personal testimonies, creating a fundamental gap in our understanding. Integrating mind and brain into a cohesive framework, which is the ultimate goal in cognitive neuroscience, becomes simply impossible without subjective accounts. EEG offers excellent temporal resolution for tracking rapid brain changes, but provides nowhere near the spatial accuracy of MRI, creating a trade-off between time precision and location precision. While MRI offers superior spatial resolution, it's much more costly and far less practical in the neurointensive care unit where dying patients are monitored, making EEG the more feasible choice. Animal models provide highly controlled experimental conditions for studying cortical dynamics, but exclude verbal responses that sample consciousness, limiting access to subjective experience. DMT administered to healthy controls has been shown to produce phenomenological features shared with near-death experiences: transcendence of the physical body, entry into alternate realms, and encounters with sentient entities. However, DMT experiences may encompass an even wider range of subjective attributes than near-death experiences. So, additional validation is needed to establish it as a genuine model of end-of-life consciousness. In a unique case report, Woollacott and Peyton chronicled Bettina Peyton's near-death experience during a 1988 surgical emergency when placental obstruction required intervention under general anesthesia. During cardiac arrest, Peyton reported heightened awareness beyond the reach of anesthetic drugs, visual perception despite taped-shut eyes, and complete absence of fear, a paradoxical state of consciousness. She described feeling truly awake for the first time, while under general anesthesia. Despite being anesthetized with eyes taped shut, Peyton reported perceiving surgery sensations, staff conversations about blood loss, blood bags on the IV pole, and awareness of her heart stopping. After the surgical complication and cardiac arrest triggered her near-death experience, both Peyton and her baby girl ultimately survived. While parts of her narrative were reportedly confirmed by hospital staff, this validation came mostly from Peyton's own interview responses 26 years later, which lacks objectivity. Peyton's near-death experience had consequential effects directly linked to fundamental changes in her identity and priorities. She transformed from a strident materialist who viewed consciousness as brain-dependent to someone who perceived consciousness as fundamental and independent of brain activity, opposite worldviews. Despite considerable hurdles in understanding brain function moments before death, we must exhaust natural explanations before invoking supernatural ones. Occam's razor demands that we first exhaust all possible natural explanations. So what happened to Emperor Augustus after he gazed into the eyes of the resurrected Lazarus? What began as the welcoming embrace of eternal space rapidly devolved into an uncanny hellscape. Augustus glimpsed the infinite that had driven lesser men to madness, and while he survived, he was never the same. As for Lazarus, he lived the rest of his life in solitude, after his eyes were burned out with hot irons by the emperor's decree, sealing away the void that others had gazed into.